bounding this helps us figure out how well the expansion approximates the actual function. Is there a way to determine like how far from the point you're approximating, like a or 0 in this case, you can go to a certain threshold?
Yeah, right, that's right. I mean, so you're asking, right, so you're asking, suppose, and you definitely could do this, right? So you're asking, you're thinking that you're thinking a slightly different situation than here, but closely related. That you have some a here, and you have a function f, and you want to, and you are willing to maybe you're willing to take some fixed large k, and then you're asking, what I'm interested in, how well does this function, this polynomial, approximate this, but I want it within an certain area, right? So there's a given epsilon, and you're interested in how far away can you go from a so that this here is less than epsilon. And so this is, so this becomes a question of this remainder term, right? So this becomes a question of this remainder term. When can you always say that this remainder term is less than epsilon? And so like in this particular case, you would have to do it on a case-by-case basis. But in this particular case, the remainder term is, right, if this interval here, in that example over there, if you have here 0, this was a in our example, and then you want to go out here to some x, and now you know that c here is between 0 and x, but you don't really know anything else, right? So then it's like this remainder term. You will have this remainder term in this example at the c here. This again was equal to this thing here over k factorial. And so you would have that, you would want this thing here, rk c, you would want this to be less than epsilon. And so you would have that this thing here, the only thing you can really do is that you can say that c is less or equal to x. Yeah, that's right. That no. So you would do. So what you would do here is you would say r k c. This here has to be bounded by because c is less than x. So this is e to the x. You have to eliminate c. So you would do like this: k factorial times x to the power k. You have to eliminate c, right? Because you don't know anything really about c. And so this here now has to be less than epsilon. So now you only have, you have fixed your k, and so now you only have one variable, and you can solve that. Right? But you really have to eliminate c. Yeah. Okay. So again, how well the Taylor expansion approximate depends on the function. Okay, the next topic is another important topic, and so this is integrals. And there are different ways of defining integrals. This here is certainly one of maybe the most natural one. And so this is what's called Riemann. So it's after German mathematician Riemann integrals. And so the thing is that here now you look at a function. You have a function on some interval from a to b into r. And this function f here is bounded. And the idea is for integrals is that, so you have a function and you want to be able to define, so define area below graph. So if this is a function, you want to be able to calculate what is this area, okay? Now, if the function was to have crossed the x-axis, then this area here would count negatively, and this area here would count positively. Anyway, so this is what you want to do, and you're always starting with a bounded function. Now, to do that, right, and so you want to define that. The only thing that you know for sure is, so there's only like one ingredient you have. So only thing you know at the outset. So the only thing you know is that if you take a right angle, so if this length here is let's call it D, and this here is E, right? Then you know that the area here, so area is D times E, right? Okay, that's the only thing we have. So now, how do we define the area below the graph? And to do that, we first need to talk about partitions. So partition. So suppose I have an interval here. A and B are real numbers, so I have an interval here. Then I talk about a partition and it's useful to have a notation for a partition, so I call it P of this interval here. This is finitely many dividing points. And the dividing points always have to start at A and end at B. So you have finitely many, let's say K many, and you're looking at, okay, I'll write it K plus 1 many. So the first one has to be A, and then you have x1 up to the last one, and that has to be B. Okay. And so, so what you are thinking about is, so you have this interval here from A to B, and you have these dividing points, and you are thinking about dividing the original interval into these subintervals, right? So these are the subintervals, right? So you divide the original interval into subintervals. And the subintervals are, I'll do it like this. I will do it where I take from, it's always from, one to the next. And I'll write it typically where I'm starting, where I'm ending at I and beginning at I minus 1. So, right, so I'm dividing it into these subintervals. And so in this case here, where this is x0, there's going to be k subintervals. Okay, and it's you only always go from one to the next, right? So that's a partition. And now we need a second notion related to this, and this is a subpartition. So subpartition. Subpartition, this is also sometimes called refinement. So a subpartition is, so if you have a partition, so P1 is a partition, and then P2 is a subpartition or refinement. If P2 has all the dividing points of P1 and then some. I mean, right. I mean, of course, it could be a trivial subpartition where P1 and P2 are the same. That's okay. But in general, it would have some more points also, some more dividing points, okay? Now, right, so now let me look at, so what is then, so now let's try to get closer to try to define this with the area below the graph. Okay. So again, we have a function f from a to b into R. We assume that this is so that is bounded. We have P here is a partition of this interval here. Then we defined an upper and a lower sum. Then we define upper and lower sums. As follows. Right, so again, you have a given function that is bounded, and you have a partition. And so we define upper and lower sums, and the upper and lower sums I will denote like this. It depends on the function, of course, and then on the partition. That's the upper sum. And the lower sum, similarly, I will denote like this. And so how are these defined? So they are defined as follows. That you have, here you have your interval from A to B. Then you have, this here is x0. Here I have x1. And here I have maybe x2. And then this thing here is then x3. So I take, I look at one of these intervals. Well, it could be this one here. It's between, in this case, it would be between x1 and x2. And I would look at the function in this interval here. And I would, so the contribution from this here would be that I would take, so for the upper sum, with respect to this partition, the one that comes from this subinterval here would be the sup of f on this subinterval here. So the sup of the function times the length of the interval. Like that. So this would be the value that in the upper that would come. In a minute I'll write it out more clearly. But this would be what is coming from here. And likewise, for the lower one, the contribution from this little interval here would be the inf of f. And then times. And the idea, right, is, okay, so that would be the contribution. The idea, of course, is that you have the only thing we knew was this with the area of a right angle, right? And so you have this function here, and you have some little interval here between xi and xi minus, xi minus 1 and xi. Right? And you're focusing on this little interval here. And you're looking at the function. The function was bounded. So there is a sup on this. And you try to look at the smallest right angle that kind of have the graph that fits, where the graph fits inside that, right? And then you're looking at, so this is the contribution from this little interval to P, to the upper sum. And then you have, right, that you're looking at the largest right angle like this that fits under the graph. And that's then contribution to the lower one, right? And the idea is that if the function is reasonable, if you're looking at finer and finer partition, then you should certainly get a better approximation to the area below the graph, right? I mean, and if the function is reasonable, these two, okay, so now what is then the, let me just define this. So this thing here, it would be convenient to the length of this interval to denote it by this. So this is xi minus 1. It's just the length of that interval. Okay, and so now written out, this thing, and then, okay, let me make one other notation. Mi is the sup of f on xi minus 1 xi. That's capital Mi. And little mi is then the inf on the same interval. Like that. And so the upper sum for this partition, this is the sum from I equal to 1 to k of mi times delta xi. That's the upper sum. And the lower sum is then the sum from I equal to 1 to k of mi delta xi. Okay, so that's the upper and the lower sum. Okay, the first thing you observe is a trivial fact, and it's, you know, that really should be the case, because one is like what fits inside the graph, below the graph. The other is, you know, where the graph fits below the right angle. So you clearly have, and this is just because this number here is the inf, this is the sup on the same interval. So you clearly have that LFP is less or equal to UFP, right? So this is clear, right? Okay. Let's look at a couple of examples. So just to make sure that this is totally clear. let me look at a couple of examples. So the first example is, so I take a function f of x equal to x squared plus 1. And my partition and the interval here, I'm going to think about this as a function on -2 to 2 into R. And my partition here is going to be -2, -1, 0, 1, and 2. Right, and so you have, so let's see, so this here, so if I draw the function, then this looks like, if this here is 1, here you have 1, then it looks sort of like this, doesn't, more or less like this. Okay, and so this means that here you have 2, and this here is -1, and here you have -2. So now, if you're looking at right, so this means here that, so this is my partition. So this means that x0 is equal to -2, x1, that's the next one, it's -1, x3 is the next one, that's 0, x4 is 1, and x5 is 2, right? And so, of course, all of these intervals here, right, they all have the same length in this case. So xi minus xi minus 1, this was what we call delta xi. This here is, for each of these, is equal to 1. And now we have that when you're looking between -2 and 2, -2 and -1, so on this interval here, the function on this interval here is decreasing, so the largest value is achieved at this point here, right? M1, this is the same as the sup of f between x0 and x1, and so this is the same as the sup of -2 to -1, right, of f. And the function was decreasing, so on this interval, so the largest value is achieved here, and that's 5. Right, so this here would be 5. And on the second interval here, right, so this is between -1 and 0, still decreasing, so the largest value is here, where it's 2. So this here is 2. And M3, this is now between 0 and 1, so now it's increasing, so the largest value is over here, so that's again 2. And then the last one is again 5. Right? And then likewise for the ones that are the infimum. So the first one, M1, well, the function was decreasing, so the smallest value is over at this endpoint. There the value is 2. So you're getting, this here is 2. And then between -1 and 0, it's still decreasing. So there the smallest is at this point where it's 1. So this is M2. And then M3, this is now, here the function is increasing, so it's still the value here. So it's still 1. And then the last one is between 1 and 2. And there it's the infimum is the value here, so that's 2. Fine. And so you see that in this case, the upper for this function, for this partition, it's this, right? All of the intervals have lengths, these small intervals have length 1, so it's just the sum of these guys, right? So this is just equal to 5. It's, if you will, it's 5 times 1, that was the length of the interval, plus 2 times 1, plus 2 times 1, plus 5 times 1. So in other words, you get here 14. And for the lower ones, it's, again, this time I want right times 1. It's the sum of those guys, and that's actually 6. Right? So, so that's upper and lower sum. Okay. Now, and we had one observation that was an immediate observation, and that was this thing here. Now, what is useful is that you're starting with a partition, and then you have a subpartition. So the next one is, so I take a function f on some interval from a to b, and this function here is bounded. And then I have p is a partition. P1, say, is a partition. And then P2 is a subpartition of P1. And now the thing that is useful is the following. That, so the following claim, the following lemma here. That if you take a subpartition, then I claim that the value of the upper sum go down and the value of the lower go up. So this is the following. So lower of f times p1, this is less or equal to the lower of f of p2. We already proved that this thing here, this one here, this inequality we haven't proved yet, but this one here we have, that this is less than the upper one for the same partition. And the second claim is that this here is then less than the upper one for the first. Okay. Now, why is this the case? This is also actually a trivial statement, but it's a very useful statement. So imagine that you have your partition P1 here, and then you have the dividing points I minus 1, and here you have I. Right? P2 is a subpartition. So there may be intervals like this where there are no further dividing points. Right? But in that case, the contribution that for the lower and upper is the same for the two partitions. Right? But should there be one or more, let's just say there's one, right? Then for the upper one, you would look at, you would then get, so you would get a new dividing point. Let's call it y. And then you would get, for the new one, you would look at the sup here on this interval here, right? But the sup on this interval here of the function is less than the sup on the larger interval. So you would get a sup of f on the interval from I minus 1 to y of f. You get that, and then you would get times the length of the interval, that's y minus xi minus 1. And then you would get a second sup, but this is now from y to xi of f, and then you would have multiple by the length of this interval. So this here is then from xi to y. Okay? So this is what you get from the new partition, the contribution from the second, this is the contribution that you get from the upper sum for this partition P2 from this part, right? But now you see that this thing here, the sup over this little interval, well, that of course is less than the sup over the larger interval. So this is less than mi, and I just keep this one here. And this one here is also a subinterval of this larger interval. So this is less than mi again, times xi minus y. But now you can factor out the mi. So you're getting mi, and you're getting the sum of these two, y minus xi minus 1 plus xi minus y. And so you see that this here is exactly mi times xi minus minus 1, right? And so you see that the contribution that we get here to the upper sum from this part here, that was this and this, those two things. This is less than the contribution we get from the upper sum from the first partition, right? And so this proves this inequality here. And this inequality is just similar, right? It's just with the int instead of the sups. Okay, so this is like a key point. It's each of these steps is like completely trivial, but together it actually means that you can really define something non-trivial. Okay, so now, and this may seem cheating. Now well, first of all, we define the upper and lower integrals. So we have upper and lower sum, and now we define the upper and lower integrals. So upper and lower integrals. Okay, so the upper lower integral, so the upper here is denoted like this. We take a bar over this, and this is the upper lower integral. So this is the integral, this is the function, and then you write this. And so this is simply defined to be the infimum over all partitions of the upper integral, upper sum, sorry. Right, and so remember again that if you take a partition and you refine it, if you're looking at a subpartition of the given partition, then this number here goes down, right? I mean, it may stay the same, but it's certainly not bigger, right? So the idea here is that essentially this number here you get by looking at finer and finer partition, right? So idea is that the infimum that this is a limit over finer and finer partition. Right, so that's the idea. It's sort of but the precise statement is that it's just the info. Right? So this is the upper integral, and then likewise we define the lower integrals.
Is there any assumption that like you have finitely many partitions, or like obviously?
Right. It's not. But there is a key assumption is that for each partitions there are only finitely many divisions. But there's not but there are infinite many partitions. So it's really and so when I say that it's a limit over finite and finite partitions, you should really think about that in sort of quotation mark. This is not a very precise statement. Okay. So but the precise statement is just that it's infinite over all partitions. Yeah. And so I mean, you can make that precise, but then that requires a lot of stuff that we don't want to do here. And there's no reason to it, because there's a perfectly reasonable way of defining it. And so that was the upper integral. So this is the upper integral. And then similarly, the lower integral. The lower integral, and there I'm just putting the bar below. And you define it like this. And this is now the soup, right? Because remember that if you took a partition and then you take a subpartition, then this lower sum actually went up. So it's a soup of all partitions of these lower. Okay. Right, and so now we say that, and then we say that, so now here's the definition, and again, this may initially seem like kind of we are wimping out, but in a minute we will then determine when this is the case. So we define, so f here. So if you have a bounded function like this, then we say that f is Riemann integral. So if the lower sum is equal to the upper sum, so if this is the case, and in that case, and then the Riemann integral is this common. So the Riemann integral is written like this, and this is just this common value. Right. Okay. Now, one thing I just want to remark is that you always have that so one remark is that so note that. So first of all, we had this trivial statement that if you take a partition, then the lower sum is less or equal to the upper sum. Right? Then we had that if you took a subpartition, if this here was a subpartition, P1. Then this lower sum here, under a subpartition, the lower sum went up, but it's still staying below. So you have this inequality here. Okay, now what is this useful for? So as a consequence of this, we get that whether or not the function is Riemann integral, you always have that the lower integral here of f dx is less or equal to the upper integral. So this here is for all functions. And why is this the case? This is because if you take this here is the sup of these lower partitions, right? But if you take any given partition, then this lower thing here is less than the upper one. Right? And so now imagine that you take, so if you take a lower partition, right, suppose now that you take the sup over all partitions, then it means that there is one partition so that this value here is close to the sup. But for this one here, right, you have this inequality here, right? And so in fact, if you take any other partition, you can think about it. Maybe I'll explain this more detailed next time because I only have a minute. But it basically comes from this inequality here is coming from this inequality here. It will take just a few minutes to explain it clearly. So maybe I'll just leave it here. But a key point here is that you have this inequality here. And it comes from that. Right? But we'll return to that next time because it's to make it really clear, it will take a few minutes. Now, the last thing I want to say is that so you may think that we sort of wimped out of saying when this right, because we just define it, we just say that it's Riemann integrable if those two things are equal, right? And so, but then the question, of course, becomes when are those two things equal, right? So that's the key question. So the key question is when are they equal? And we'll answer this next time, where we will show that if f is continuous, then they're equal. Okay. And so anyway, so I'll return to this. I will first, we need anyway some more information about this upper and lower integral, and I will first show why the lower one is less or equal to the lower one is less or equal to the upper one always, right? And then we will talk about, some criteria for when they are equal, and then we will prove this for continuous functions.
Is that an if and only if, or are there other cases?
No, it's not. It's not. It's not. It's not a total answer. It's a good initial answer. But there are many functions that are not continuous, that are very worth, that plays key roles, and they're still. And we will also look at an example. It's in the notes, but I didn't get to it. We look at an example of a function that is not where you don't have this equality, and this is like an old